So in time complexity, there is also something called as order of log n, and in that what happens is that whenever you're running your code breaks the operations steps, the number of steps to be taken, into smaller steps. And how does that work? So imagine you have a dictionary and you want to find a particular word in that, and in you try to search it. For example, let's say the word is euphoria and you have the letter E, so you try to go to that particular page, the letter E, where E is there, you know exactly that word will be there, you try to find it. Same way here also you do the same thing, and whatever is like behind that letter, like whatever letters were behind, you don't go through those letters because you're sure that E comes later on, because before E whatever letters are there, they won't have the word what you're searching for. This is the exact same way how your what you say code also does the operation. So take an example of binary search. I'll show an example here itself. Yeah, so you can look at this to get a clear understanding of what I'm saying. So let's say I'm trying to find the number 700 and I'm using binary search, and here you see binary search takes the starting 2 points, the starting point and the end point. It sums it up, so the index position from 0 up to 31 plus 31, and it divides by 2. And here when I say the next step, okay, we get the midpoint. So when you divide by 2, we take start stop plus, we sum it and we divide by 2, so 30 by 2 we get 15. So we'll see we get the midpoint as 15. And now from this index position, so at 15 the index position is 417, okay, and the number that we want to find is 700. Notice that in binary search we keep the numbers in ascending order. So here it's from the range from 0 to 1000, and you know some numbers are missing in between, but that's totally fine. We'll go from 2, 11, 68, 74, it going up to 976, and our target is to find 700. If it is present, it's gonna find it. If it's not, it's not gonna find it. So we can see that 700 is present at the index position 26, okay. And now we took the midpoint, we are at this one. What's the next step? We know that just like how you know in dictionary that you know at E itself you have it, you don't have to go behind, because you know you're sure that euphoria don't come anywhere in other letters, it comes at the letter E. So here also same way, you know that after 417 itself, we go further on, we'll get 700. If you go behind 417, we are not gonna reach 700. So we step forward, we'll see the next step. Okay, we know that we are at the midpoint here. Then again step forward. Now you see we took from the midpoint one step ahead. So we took the next value, the index position, and the last index position, and now we are going to take again the midpoint of these two values. So we'll sum these two index positions and then we'll divide by 2. So now you see, step forward, we will get it as 23. So the midpoint of these two values in between this range is 23, and at the index position 23 we have 673 as the actual value, and you know that 700 comes right side because after 673, not behind 673. So we go again, step forward, go again, take the midpoint, repeat the same process, we get the midpoint as 27. At the index position 27, it is 854. Now at 854, you know that if you go right side, you won't get close to your actual value, which is 700. You have to go behind. So see, I'll step forward. You know that your decision should be in the left side. Now you see that your endpoint has come towards this side, towards the left side. Now you check, you take the midpoint again, and you get your actual answer. So literally at index position 26 you got the value 700, and you did that with breaking down the steps into lesser ones. If at all you were using your for loop, though that is nothing but your order of n, you see that you have to iterate through all these index positions 0, 1, 2, 3, 4. You literally kept on searching until 700, if at all you had 700 values behind it. So that is much slower. What if you had a million values? Because if at all you had a million values and you are using binary search, which is at the time complexity of order of log n, it will be much faster, very faster. So this is what also this order of log n comes very faster and it's very efficient of order of 1, the constant order of 1. Okay. So the next one that we are going to see is order of n log n. So here we'll take an example of merge sort, and this n log n is very similar to log n. It's just that log n order of log n is repeated n times. That's why it's called as order of n log n. So here in merge sort, we'll take the example. I'll start this example. You can see it in my screen. I'm starting this merge sort. Same way, similar to binary search, we divide this array from index position 0 to 9. I have taken the array size as 10, and here we have random values, and in merge sort we are literally trying to arrange them in ascending order. So dividing array from index position 0 to 9. So 0 to 9 we have 10 values here, and I'm thinking we'll take the first division as 0 to 4, so 5 values on the left side and 5 values to the right side. So here you can see dividing array from index position 0 to 4. Yes, exactly what I said. And then we are saying dividing array from index 0 to 1, because now when we divided it from 0 to 4, you can see 1, 2, 3, 4, 5. 5 values are towards the left side, and these 5 values you will take the starting first and second value, keep it towards left, and then you will take third and fourth, keep it towards your right. You will make a little tree out of it. Imagine it like a tree, binary tree. And the 39, it is your third value, or 0, 1, 2, second value to be exact, will be like your main node. Okay. And now if I started, you can see merging two sorted halves starting at index 0. So you can see the highlighted ones, 71 and 41. We are trying to arrange them in ascending order. So 41 comes towards the left and 71 comes towards the right. And again, we will take index position 2 and 4, which is 50 and 39, and merging two sorted halves starting at index position 3. Okay. So you can see 39 and 50 will be arranged exactly what I said in ascending order. And then we will compare this 39 39, it's okay. Then 39 50. So these all three are in a proper alignment. Then we'll compare with the 41 and 71. So 41 and 39 seems like they have to change. So you can see how it works. Exactly. So now you notice that in binary search we were just dividing by 2, then going on searching for our value in binary search. Here same thing, that was in binary search it was log n, but when it comes to n log n, same log n is repeated n times. You can see how many steps we literally did to actually get it in ascending order. And this one is more, the time complexity is more for this one, n log n compared to log n. Yeah. So if I keep going on with more steps, you can see it takes a lot of steps to make it into ascending order. So yeah, in the end you'll get it. So now we are going to see that there is something called as order of 2 to the power n. So in this one, what happens is that you can take an example of a Fibonacci series, or recursive function here. I have written a recursive function on my screen, you can see that, and it is literally calling itself. Recursion is nothing but calling the function itself. But notice that whenever you're calling this function, let's say the argument that I'm passing in is 10 for the particular function that I created, and n will be 10, so the first if condition won't work, and it goes to the second return statement, which is nothing but Fibonacci of n minus 1 plus Fibonacci of n minus 2. Now we have to find what is n minus 1. We don't know what that function does, so we literally pass, n is nothing but your actual argument that you pass 10, so it will be 10 minus 1 and Fibonacci of 10 minus 2. So you are passing Fibonacci of 9 and Fibonacci of 8. Then you stack this up. You don't know what is Fibonacci of 9 and Fibonacci of 8. You literally went to that function. Again the same thing repeats. You check if the n is less than or equal to 1. It is 8 now. Literally go again to the return statement. Now it becomes 7, 6. Again it becomes 5, 4. Again it goes 3, 2. Again it goes, when it reaches less than or equal to 1, that's where it returns n. So now when it returns n should be now added up. Everything will be added, because as you kept on going in that loop, you found all other calls and you just stack them up together That's how this function is working. So now this is literally an example of how your what you say recursive calls are in the powers, 2 powers of n. So n is nothing but your argument what you're passing in. So it was in 2 to the power of 10, you can say. And what if I give 100 here? You can see how hectic this can be. Yeah, it's going to loop on, going on, calling, and yeah, just